In reviewing the properties of exponents so that you can complete your homework problems, let's begin by looking at the basic properties of arithmetic that you learned in your algebra course, hopefully in high school. And we want to establish the fact here that the addition process is related to the multiplication process in the same way that the multiplication process is related to the exponential function. And we actually can get between all three through sequential application of the processes. So let's look at the examples that we have below, and we notice here that when we add the same base together 3 times, that gives us our multiplication process through realizing that the base times the number of times that it's added gives us the result here. And variables correspondingly do the same thing. You have the base, the multiplication by the number of times it appears, and you get the resulting answer, in this case 3x. Similarly, the exponential process, the power is obtained through an analogous procedure. So we look here, 3 times 3 times 3. Our base is 3. It is multiplied together 3 times, giving us our power, and 3 to the third power gives us 27. And variables work in an analogous fashion. So you have the base x multiplied together 3 times and end up with x cubed as your result. Now from this we can extract several rules for dealing with exponents. When you have like bases and like powers added together, this is the same as the traditional multiplication process. In this case, your base is x squared, and we see that it is added together 2 times, giving us 2 times x squared as our result. When we have identical bases, whether or not the powers are the same, we can actually combine these through the operation of adding the powers together. And so in this case, this is x to the 5th, and just one time I'll expand this out to show you that it does indeed give us the result that we want. In this case, you have 5 times or 5 copies of the base x multiplied together, and we get the same answer. Raising a power to a power is analogous to the multiplication process, and therefore we extract our rule where we see x cubed times x cubed. We add our exponents together, that gives us x to the 6th. We could also have realized that 2 times 3 would give us 6 and give us the corresponding same answer. We will establish this rule here in just a few minutes. When we have a negative exponent, this is the transition between the denominator and the numerator of a fraction. So x to the minus 5 is the equivalent of writing 1 over x to the 5th. And all of your other multiplication and addition rules for variables and exponents still apply here. So if we look at our first example here, we'll break it down the way that we normally would have in a high school algebra course, just for illustration purposes. And then we can cancel out from top to bottom, giving us the remaining component, which is just x. But we want to do this a little bit more elegantly, and so we can do this one of a couple of ways. We can bring the power up from the denominator, and now we have the same base multiplied together, so we can add them together, and algebraically we know that this gives us x to the first power, which is just x. Or we can build our rule that says when we have like bases on the opposite side of a fraction bar, they are subtracted, or the exponents are subtracted, and we get the same answer from 3 different perspectives here. So what if we have different bases? When we have different bases, whether or not the exponents are the same or different, if we have different bases added together, there is not a mathematical guarantee that we're going to be able to do anything. You may be able to change out a variable, you may be able to do something that allows you to simplify it, but as a general rule, you will not necessarily be able to do anything. When we have different bases multiplied together or correspondingly divided, but they carry the same exponent, we can simplify by bringing the bases together to a common exponent. And I encourage you to verify this for yourself by expanding this out using the commutative property of multiplication to rearrange and create 3 identical xy factors in this example. So you should be able to verify that on your own. If we have different bases multiplied to different powers, We may be able to extract a common factor. In this case, we can extract out an xy to the common power of 2 and leaving a single x on the outside. It all depends on whether this will be beneficial to you or not in the problem as to whether or not you should do this. But when we have different bases multiplied together with different powers, the most we're going to be able to do is extract a common factor. And so in summary, let's look at some of our rules here. When we have identical bases multiplied together, the powers will add together. When we have a base raised to a power raised to another power, the exponents multiply together. When we have different bases multiplied together by the same power, we can create a common base raised to that power. And the same thing with the fractions. We can create a common fraction to that identical power. When we have different bases to different powers added together, there is no guarantee that we will be able to do anything. Again, we may be able to rearrange, or we may just have to deal with it in its present form. Please see the following 2 example videos for some specific applications of these exponent rules.